Yes, hello everyone. So now we are discussing a question again on EMI. This is so please look at the question first of all. It says a conducting rod of length L moves with velocity V parallel to a long wire carrying steady current I. The axis of the rod is maintained perpendicular to the wire. Okay, with near end of the end a distance r away as shown in the figure. Find the magnitude of the EMF induced in the rod. So they are giving basically a simple diagram. This is like a fundamental question that all of the students, right, all students should be knowing how to solve this, because these kind of questions in JE they ask repeatedly. So you are having a rod like this. The distance between the wire and the rod is r, and the length of the wire is L. The velocity with which the rod is moving is V. Okay, and the current in that wire is I. They are interested in finding the total EMF developed inside, right? Yes, the magnitude of the EMF induced in the rod. They are asking you to find that. So if you are interested in finding the EMF induced in the rod, it's very easy. So for that, what we can do is we can say that each section of this rod will be having one EMF. Why like that? Because if you think of the magnetic field induced by or magnetic field produced by this current, that magnetic field formula would be B is equals to mu naught I by 2 pi r, or let's call it as 2 pi x. That means it changes with the x at which we are talking. So if I am at a distance x here, I'll have a particular magnetic field. If I move further away, I'll have a smaller and smaller decreased value of magnetic field. If I go to the left side, I'll be having a bigger and bigger like that. So basically, I'll go at a distance x. I'll take a small section as usual, a dx. I can find out the EMF for this dx section by using the formula E is equals to BLV. This formula we are having motional EMF. Because I am finding for a small section, I can call the EMF as DE is equals to B into L. For the small section I am finding, that is dx into V, the velocity. Because it's a translational motion, each particle in this rod would be having the same velocity V. Okay, so this is EMF produced by this small section. Like that, how many sections are having, you can think that, right? And what about the EMF direction? That means which side is plus and which side is minus. You can find that by using the Fleming's left hand rule, right? Magnetic field produced by this wire would be inwards at this location. This is the direction of the magnetic field produced. Then what is the direction of the EMF? So left hand side Fleming rule, if I use, I am finding that this side will remain positive, become positive, and this side will become negative. So that means the entire rod will now behave like a combination of cells, we can say, like this. Like this, infinite number of cells would be there along the rod. Each cell is having an EMF of DE. That is the DE I have calculated. Like that, many DEs are there. Because they are in series, I should be adding all of them and I'll be getting the total EMF. So the total EMF would be nothing but integration of DE. That will be integration of B value I can substitute. So when I substitute that, I'll be getting the constants out. Mu naught IV divided by 2 pi integration of 1 by x dx. The limits of my integration would be going from where to where? My starting of integration would be from r until the last length, last point of my rod would be r plus L. So I'll go from r to r plus L, and I'll be getting E is equals to mu naught IV divided by 2 pi. 1 by x would become natural log of x, limit going from r to r plus L. And therefore finally I'll be getting E is equals to mu naught IV divided by 2 pi, and this would become natural log of r plus L divided by r. That's it. This is the total EMF induced in this. Okay, a common question that they ask in the JE examination, this kind. So we'll stop here then. Thank you.